Okay, let's continue our discussion. So in the last video, we have discussed law of orbits. Now we are going to discuss law of areas. So let me introduce what does it mean, and then we will come to explanation part. So let's say this is an elliptical orbit, and this is Sun at one of the two foci. There should be another focus here. Now consider there is a planet, and the planet is revolving around the Sun on this elliptical path. So let's say from this point, it comes to a new point here, new position, you can say. So if you observe its motion, and if you draw an imaginary line which is connecting the sun to the planet, this line is going to sweep area. And let's say this is area, okay, our planet is bit ahead. So let's say it is reaching here. Okay, so this area, let's say this area is delta A1, and the time taken to reach from here to here, this is delta T1. Okay, now let's take another situation here. Again, this planet is at this point and it moves from here to a new position here. So now we are considering another area swept by this line joining the planet to the sun. And let's say this area is delta A2, and the time taken to reach from here to here is delta T2. Now, what does law of area says? It says that if delta T1 is equal to delta T2, that is, time taken to reach from here to here is equal to the time taken to reach from here to here. If these two time intervals are equal, then the area swept, that is delta A1, should be equal to delta A2. This is what, if you express this thing in words, then this will be law of areas, and this is a mathematical expression for the same. Okay, now coming to the explanation part. How can we say that? So let's consider this part of its motion only. So here, what is happening? This is the position of planet, and let's say this is the position of planet after it moves. Okay, so from here, let's say this position is T1 prime, and this position is T2 prime, and this is the trajectory between these 2 points. And if we take its velocity, it will be tangential. Let's say this is v, vector v more precisely. And then we have a time interval delta t. In general, here we were taking delta t1, delta t2 because we were comparing the two situations. So if we are taking only one situation here, so no need to write delta t1 or delta t2. And let's take this area is delta a, and you can express it as area vector. And the direction of this area, look, its magnitude is the area itself here, and its direction is, you can obtain the direction by using right hand. So you have to curl the four fingers stressed and the thumb making perpendicular to the four fingers, and you can curl those four fingers along the direction of its movement, and then the thumb will indicate the area vector here. So we are taking anti-clockwise movement here, and our area vector, for this area vector, the direction of area vector is perpendicularly outward to the screen in this particular case. Okay, let's say this is mean distance from here to here. Let's say this is r. So if this is not moving for a very long span, so this r will be nearly equal to this one. So let's say these two lengths are nearly equal, means not exactly, but yeah, r, and this is r plus something delta r. It will be better. So I'm removing this one. Okay, so this is r plus delta r. Now we can express delta a equals to 1 by 2. And look, if this is very short interval, so we can consider this figure here as a triangle, or you can say it is a right angled triangle. We can consider this P1 prime, P2 prime to be a straight. Okay, let me use some different thing. So you can consider this P1 prime and P2 prime to be a straight, and then you can consider that this is nearly perpendicular, and in that case, this will resemble a right angled triangle, and you can write its area as delta A equals to 1 by 2, and this will be R times, here we are using cross product, mind it, here we are using cross product, and this will be, let's say this is L, this length is L, so it will be L. And now 1 by 2 R cross L can be written as velocity vector V multiplied with delta t, and then we will have 1 by 2 R cross V equals to delta A divided by delta T. Here, I have divided both sides by delta T. So, we will get this thing here. Now, continuing this part. 1 by 2, if I am doing multiplication in denominator as well as in numerator here, so it will be R cross V into M, and M is scalar quantity, so no need to worry about its position where I am placing. Now we can write this is R cross MV, and then we can write 1 by 2 M, and this will be R cross P, linear momentum of the planet here. And then we will have delta A divided by delta T equals to 1 by 2M into angular momentum here, vector. Now R cross T is L. So you can write here angular momentum. Now, in this particular system, look, this is an isolated system of a sun and a planet. So in this particular system, there is no net external torque acting on the system. So if there is no net external torque, the angular momentum should be conserved. And with this argument, we can say that this L is a constant here. So you can write delta A divided by delta T is a constant, and further you can write delta A by delta T is constant. Now we have arrived at the same situation. If this is constant, it means delta A1 by delta T1 equals to delta A2 by delta T2, and if you are taking some more instances, you can go up to n number of such instances. So let's say delta An by delta Tn, and this is what we have earlier discussed, law of time period. So let's say this is third, law of time period, or simply law of period. So we can write law of periods. Okay. So what does it say? If A is the semi-major axis, we have discussed this thing, semi-major axis, and T is the time period of revolution, time of one complete revolution. Okay. So this law states that a square of time period is directly proportional to the cube of semi-major axis. This is what. Or you can write T square divided by A cube is constant. So this will help you if you know time period of a planet and its semi-major axis, and if you know the semi-major axis of another planet of the same system, you can state its time period, or you can, if you have time period known, you can say what is the length of its semi-major axis. This is also going to be In the same way, if there is one planet here, you can write this thing for one planet, and it's if there is another planet in the same solar system, so the same argument will be for the second planet as well. So if you know three out of these four parameters, you can obtain the fourth one. So this is what law of periods, and you can write in words if you want to write its definition. Okay, now explanation for this part. So it will be a bit easier if you observe the data extracted. So I'm trying to bring that for you here. Okay. Okay. So here we have the data, and this is from your NCERT textbook. So you can see this is length of semi-major axis, this is time period, and this is the constant, this constant here, Q. And you can see that it is coming nearly 3 units. So this constant C is nearly 3 units. And the actual, if you want to go for actual, it will be 3 into 10 to the power minus 34. And you can say what its SI units should be by comparing these two quantities. So I am leaving that part to you. And in case there is an issue, I'm going to say it in the next class. But I guess till now, you should be able to understand what should be its unit. If you know the unit, SI unit of this and SI unit of this, you can obtain the SI unit for this constant also. So this is its magnitude. Okay, this is all for this video. In the next video, we will see an example.